Hello everyone, my name is Kangping Hu and I'm a PhD student at Brown University. Today I'm going to present our work on a fringe field shaping CMOS capacitive sensor array, and we are very excited to be part of IEEE Sensors 2021. Impedance spectroscopy is a common technique used to study electrochemical processes at electrodes. It can also be used to detect cells growing on electrode surface as shown in the left figure. More recently, it has been extended to dense CMOS arrays, which can produce impedance images. For example, the red figure shows one of our previous works to image the impedance of bacterial colonies with a 512 by 256 CMOS sensor array. EIS measurements are fundamentally measuring the local electrical environment around each pixel. When the electrode area is small and at high measurement frequencies, much of the electrical response is actually in the fringing field, extending outward from the pixel. And once we have a dense array of microelectrodes, those fringing fields are influenced by all of the neighboring pixels. Here is an example of electrostatic simulation showing how the electric field is affected by the bias applied to other nearby electrodes. These multi-electrode patterns offer a new opportunity to shape the applied electric fields and therefore change the sensitivity of the EIS imaging sensor. Here is a simplified model to expand the concept of fringing field shaping. We have two pixels, pixel 1 and pixel 2, while each pixel is driven by one set of non-overlapping clocks with some phase offset. One side of both pixels is biased to B bias, while the other side is biased to VCM and V standby respectively. C1, C2, and Cm are the capacitance seen by pixel 1, pixel 2, and the mutual capacitance. When the two sets of switching clocks are offset by 90 degrees, we can derive the equation for I-sense as shown on the right. And inside this equation, we can tune the phase offset, output bias voltages, and the switching frequency. Here are three kernel examples with 5 by 5 pixel blocks, while theta1, theta2, and theta3 have different phase offsets, such that these blocks can be configured into radial, vertical, and horizontal arrangements. Here is the sensor array to implement the fringe field shaping. This array has 100 by 100 pixels with 10 micron pitch. Each pixel can be driven by one of the three non-overlapping switching clocks. To suppress valve noise and offset, we use chopping switches and a pair of integrators for readout. The table of switching clocks and the row and column controls are shown on the top right to implement the three types of kernels that we described before. This EIS sensor array uses 180 nanometer CMOS process. We chemically etched away the top aluminum metal layer and used the underneath titanium nitride diffusion barrier layer as electrode. Here we show the measurement with 20 micron polystyrene beads. The two figures on the top show the microscope image and the impedance image with no fringe field shaping, while the three figures on the bottom show the radial, horizontal, and vertical fringe field shaping. The switching clock is at 50 MHz. We can observe that with fringe field shaping, the normalized 2D autocorrelation approximates the spatial impulse response and correlate to each programmed kernel. Then we sweep the phase offset with standby, switching frequency, and the different kernel type with a total of 324 different combinations, and use the normalized variance, a commonly used autofocus metric in optical microscopy, to rank these settings. We can observe that in addition to simply detecting these beads, some settings produce qualitatively different images, which may correspond to sub-pixel bead locations or subtle variations between the size or shape of different beads. In conclusion, we propose a CMOS capacitive sensing array with unique fringe field shaping capabilities, and we use polystyrene beads to demonstrate the diversified pixel scale features and improved sensing performance. Of course, there are many ways to explore and improve. One of the directions is to use the fringe field patterns for microscale object classification and 3D shape reconstruction, and our next sensing chip is underway. Last but not least, I would like to extend my thanks to DARPA and NSF for funding this project, and our collaborators for their help. With that concludes my presentation. Thank you.